Okay guys, we're going to start chapter 7 today. It's about energy. It's one of my favorite chapters, and I hope that as we go throughout this chapter, you'll understand energy a lot better, and it'll be something that you really like to learn about as well. So let's get started. I would like you to have your chapter 7 guided notes out. There's quite a bit to fill in this video in your guided notes, so please have those out. Before we get to the guided notes though, let's look at this slide here. I've just put up a number of pictures that remind me of energy, and I'd like to go through them briefly. So let's start right here with the pizza. And pizza has energy, of course, that's how we get our energy, but it's got energy in chemical bonds. In the bonds in this pizza, our bodies break it down and we use that energy and we convert it into the energy that we need to do our daily activities. But a lot of it is also going into heating up our bodies. And so, our bodies are at 98.6 degrees Fahrenheit, and the room temperature you're in right now is probably around 72. And so we've got to have energy in order for that body heat to be generated, which is essential for life. Okay, I've also got a picture of IPP. For us here in Delta, we're very familiar with IPP, but it uses chemical energy from coal. And we burn that coal, and it heats up the water. The water that's heated up, it goes to steam, and the steam turns the electric generator, and it produces electricity. And so we're using coal, the chemical energy in coal, to produce electrical energy that way. I've also got a picture of a nuclear power plant. And I wanted to contrast that to IPP, a coal-powered power plant. In a nuclear power plant, it's very similar. The only difference lies in how you heat the water up. In a nuclear power plant, they're heating the water with nuclear reactions, fission reactions. So they're splitting the atom, and it releases a lot of heat, which heats the water. Water goes to steam. The steam turns the generator and produces electrical energy. So the only difference is IPP is burning coal to heat the water, and in nuclear power plants, they do nuclear reactions. So, all right, and I've got a picture here of a rubber band. When you stretch a rubber band, you're actually giving it elastic potential energy. Because of the elasticity of the rubber band, it's got potential energy. If you was to let this go, that energy would be transferred and it would move. And so elastic potential energy there. And there's also potential energy in this rock, this big boulder that's sitting on the edge of a cliff. This one's called gravitational potential energy. Because it's above the ground at some height, it has gravitational potential energy. If you were to shove this boulder off the cliff, that potential energy would be transferred into kinetic energy as it moved down the hill. All right, I've got a picture of a battery. Batteries store chemical energy, and that chemical energy is stored until you use it. You put this battery in a device, and then that chemical energy is turned into electrical energy, so moving electrons from one side of the battery to the other side. So that's an example of energy. Some solar panels are taking solar energy from the sun and converting it into electrical energy, and these windmills are taking the wind energy and converting it into electrical energy as well. So we're going to talk a ton about energy and what it is. So please have your notes out. Let's get started. Okay, so I thought we should start here. What is energy? Actually, energy is a pretty common term in science, but it's very difficult for many people to define. It's kind of an abstract term, energy. So the definition that I like best, and I hope you're writing down your guided notes right now, is this one. Energy is the ability to do work or produce heat. So it's the ability to do work or produce heat. We're going to talk about energy in terms of work in this video. In the next video, we'll talk about energy in terms of heat. And so energy is the ability to do work or produce heat. So first of all, what is work? Work, if you were to calculate it, is a force on an object, and the object moves a distance. It moves. So if you put a force on an object and it moves a certain amount of distance, you have done work on that object. And so that is how you calculate work, a force times a distance. So let's talk about the units of work. Force is measured in newtons, and distance that the object moves is measured in meters. So the units of work are what we call a Newton meter. We're not going to really go off of a Newton meter because 1 Newton meter is equal to a J. This J stands for something. Okay. J stands for joule. This is one of our vocab words for this chapter. It's abbreviated capital J for joule, and it's the SI base unit for energy. So it is the SI base unit for energy. So anytime we are calculating energy, we're going to be calculating it in this unit right here called the joule. Before we move on, I wanted to give you an idea about how much energy is 1 joule. So if you think about a medium-sized apple, okay, that's a pretty bad apple, but anyway, there's my apple. And we've talked about this before. An apple has the weight of about 1 newton when we talked about newtons. So if you were to do a joule, 1 joule worth of work, what that means is you would have to lift 1 newton. So if we lifted this apple, and we lifted it up to here, which is 1 meter above where it is now, you will have done 1 Newton meter worth of work, which is also 1 joule. Okay? So 1 joule is not that much energy. As you can imagine, it's not that much energy to lift an apple 1 meter. So it's a very small unit of measurement in terms of energy. And in fact, a lot of times what you'll see in chemistry textbooks and worksheets that you're going to do is we're going to measure energy in terms of kilojoules, which is abbreviated kJ. And that's 1,000 joules. So anyway, I wanted to give you an idea of what, how much 1 joule is in energy. So, okay, let's move on. So if we talk about work, there's a way to calculate it. Okay, this equation we're going to use it all day. Work is equal to a force times a distance. So work is done when a force is applied on an object over a distance. So you have done work on something if you apply a force to it and that object moves a certain amount of distance. Okay, the applied force has to be parallel to the direction of movement. Okay, this is so important. I'm going to put a little star by this. Hopefully you've got that in your book. But your force, your applied force, has to be parallel to the direction of movement. And we'll explain that in just a second. So if they are not in the same direction, so if your force and the direction that the object moves is not in the same direction, then only the component of force that is in the direction of movement does any work. So if your force is acting on some angle, we're going to have to find the component of that force that's in the same direction that the object is moving. Okay. Let me see if I can explain that with some pictures here. So suppose we have a force that is at a downward angle on this box. So we're going to put a force on this box right here. Okay. But my force is at this downward angle. And notice that the box is on the ground, and so the box is going to move in this direction. So when we calculate work, work is equal to a force times a distance. But remember, the force has to be parallel to the direction of the movement. So the force that we're looking for has to be parallel to the direction it moves. And if you notice here, my force is at an angle. So what we're going to do is use some trig. Okay? We're going to have to come up with some components of this force. So we're going to make the components of this force with a triangle. And if my hypotenuse is the force, I'm going to call this the force in the x direction because it's along the x-axis. I'm going to call this component of the force F sub y because it's on the y-axis. So let me ask you this. Which component of this force is in the same direction as the object is moving, or parallel to that? Okay, and hopefully you're thinking, or you're saying to yourself, it's force sub x is in the same direction. Okay, because this is going in the same direction as the object is moving. That's the one that we'll use to calculate force. Okay. So hopefully you remember your trig functions, because to find f of x, we're going to have to use trigonometry. You're going to know the angle here, and if you know the angle and you know the hypotenuse, you should be able to find f of x. Okay, let me remind you of the trig functions. So, ka, toa. So if we want this side, which is the adjacent side next to theta, it's the side next to theta, and we have the hypotenuse, so we want adjacent and we have hypotenuse, we're going to use the cosine function. It's adjacent and hypotenuse. So to find the cosine of, so here's how we do this. The cosine of theta is equal to adjacent, which is force in the x direction, divided by the hypotenuse, which is the force. Okay? And so if you solve this equation for force sub x, you're going to times both sides by f. Okay, it cancels out on that side. So force in the x direction is really equal to the force times the cosine of theta. And that's the force that you need in order to calculate work. So work, if you go back to that equation, is equal to a force times a distance. Since f of x is the component of that force in the same direction as the movement of the object, we will use that. And so we could substitute this in, force cosine of theta times the distance that it moves, and that will calculate work. Anyway, we're going to go through a lot of examples. I just wanted to give you a little preview of that little trick there. So practice problem number 1. I think I've got 5 practice problems in this video on calculating work. So please pay attention, and I promise you'll understand it, and it will be pretty easy for you. So please be following along in your guided notes. Practice problem number 1. It says a dog pulls a 40-kilogram wagon with a force of 300 newtons over a distance of 50 meters. How much work is done by the dog? Okay, so we're calculating work. What I like to do is draw a picture first of this scenario. Okay, so the dog is pulling a wagon. I'm not a very good artist, but here's my wagon. Okay, the dog is pulling it. So there's my dog. Okay, it says that the wagon is a mass of 40 kgs, a force of 300 newtons is what he's pulling it with. So there must be some tension in this rope, or maybe it's the actual handle of the wagon that's attached to the dog. It's got 300 newtons of force there. And this dog is going to move it a total of 50 meters. Okay. There's my picture. I've labeled everything, and now let's answer the question. What's the work? How much work is done by the dog? Well, I gave you the equation for work. Work is equal to a force times a distance. And remember, the force has to be in the same direction or parallel to the movement. And it is in this case. So the force is directly parallel to the movement of this wagon. And so we can just use that force, 300. And we're going to times that by the distance, which was 50. Okay, and so that's 15,000. And it's a Newton meter, or in other words, it's a joule. I hope that you just write joules on these problems, because that's the unit that's used most often. Okay? So the work done by the dog would have been 15,000 joules. Okay. Very easy. Let's go to practice problem number 2. A 60,000 kilogram jet exerts a force of 1 million newtons over a distance of 70 meters. How much work is done by the jet? Okay, I would like you guys to try this one on your own. Again, how I would do it is draw a picture, label all of the variables that it lists there in the problem, write the equation down. Again, you're going to be solving for how much work is done by the jet, and then substitute in your variables and see if you can get it. So I'm going to hit pause. I hope that you're hitting pause right now and trying it on your own as well. Okay, let's see how you did with this one. I would draw a picture, and I'm not a very good artist, so here's my jet. Okay, there's my jet. It's got the mass of 60,000 kilograms. I'm just going to list that there. It exerts a force, so it's got a force of 1 million newtons. Okay, a very large force there. Over a distance of 70 meters. Okay. So now that I've got my picture, I've labeled all the variables. Now I'm going to answer the question, how much work is done? Well, we've got the equation for work. It's a force times a distance. The force here was 1 million newtons. And we're going to times that by the distance, which was 70 meters. And so we're going to have a Newton meter or joules here. And so the answer, obviously, for work is 70 million joules worth of work. Okay, hopefully you got that answer. I wanted to bring your attention to this as well. It gave us the mass of the jet, but I hope that you realize in the work equation, in this equation for calculating work, we don't use mass. And so don't let that confuse you. That was just thrown in. It was an extra. And sometimes they do that. We don't need it though. Okay, we just need a force times a distance. Okay, let's go to practice problem number 3. Now this one, I want you to try it on your own as well. Let's give you some time here to try this one. So please hit pause on your video. See if you can't get the answer. This is a little different question here, so see if you can't come up with the answer. Once you do have the answer, hit play and see if you got it right. Okay, let's see how you guys did. It says a bicyclist exerts 30,000 joules of work while traveling with a force of 10,000 newtons. How much distance was covered by the bicyclist? All right, let's draw a picture. I'm not the best at drawing pictures, especially of bikes, but anyway. Okay, there's my bike, very simple. Okay, he exerts 30,000 joules of work. So 30,000, I'm going to list that here, joules of work while traveling with a force of 10,000 newtons. That seems a bit extreme for a bicycle, but anyway, let's go with it. 10,000 newtons worth of force. How much distance was covered by the bicyclist? So we want to know how many meters this bicyclist went. Okay. All right. Well, we know we have joules and we have a force and it wants distance. So there's an equation, the work equation, which has all of those values in it. Okay. So let's write down the equation for work. It's a force times a distance. The work in this case, whenever you see joules, that's an energy value. That's the amount of work that was done. So 30,000 goes in for work is equal to, the force here was 10,000, and we're going to times that by distance. So now all we have to do is solve this equation for D. Okay, to get the 10,000 off this side, we need to divide by 10,000. So divide both sides by 10,000. Over here it cancels out, and so the distance that this bicyclist went is 30,000 divided by 10,000, which is 3. Okay. Now the units here are very important. Remember that the units for force is in Newton. The units for distance is always going to be in meters. Okay, so we need to put the units as well. So that bicyclist would have went only 3 meters to exert that much work or energy. All right, let's go to practice problem number 4. This one's a little bit different, so I'd like to go through this one with you. It says a 120 Newton sled and rider is pulled by a 200 Newton force for 100 meters. The force acts at a 60-degree angle with the ground. How much work is done by the applied force? Okay, now this one already has a picture for us. So let's just go through and label this, this picture with all of the variables that it gave us. First of all, 120 Newton sled and rider. That's a force. And what they're telling us here is that's the weight. So if we calculated the weight here, which is equal to mg, that weight would be 120 newtons. Okay? I'm not sure if I'm going to use that, but anyway, that's what 120 Newton sled and rider means. Okay, it says it's pulled by a 200 Newton force for 100 meters, and the force acts at a 60-degree angle. Well, here's my 60-degree angle, so this must be the force that it's talking about. So I'm going to put 200 along that force vector right there. And it moves for 100 meters. So it's being pulled and it's traveling down here 100 meters. Okay. Now let's answer the question, how much work is done by the applied force? So work, let's write the equation, is equal to a force times the distance. Now the part that you need to be careful of in this problem is making sure that the force and the distance are parallel to each other. So we know that it's being pulled along the ground, so its movement is in this direction. But the force is going at an angle up at 60 degrees, so they're not parallel, are they? So I hope that you guys recognize that. So we can't use this 200 Newton value here for the force. We need to find the component of force that is parallel to the movement. And so if this is my force, I'm going to call this component F sub x, and I'm going to call this one F sub y. And we can use trigonometry to solve for these values. But which one will I want? Okay, the component of the force that's parallel to the movement is Fx, force in the x direction. So let's use trigonometry to solve for that. Okay? If this is my angle right here, 60 degrees, I need the adjacent and I have hypotenuse. So that's going to be cosine of 60 degrees is equal to the adjacent side, which is Fx, divided by the hypotenuse, which I do have a magnitude of 200 newtons here. Okay? So now let's just solve this equation for Fx. If we times both sides by 2, let's see. If we times both sides by 200, we're going to cancel that out on the right side, and so Fx is equal to 200 times the cosine of 60 degrees. Okay, so let's grab our calculator and make sure. I think that the cosine of 60 is 1/2. Cosine of 60 is equal to 1/2, and then times it by 200 is 100. So Fx is equal to 100 newtons. So yeah, this force was 200, but it was going at an angle that was not parallel to the direction of its movement. So we had to solve for Fx, which is 100 newtons. So when we come over here to my work equation, when we plug in work, the force that we put in is going to be 100 times the distance that it moved was also 100. And so the work that was done was 10,000 joules, Newton meters, so joules. So hopefully that kind of makes sense, guys. Always, if this force is at an angle, we're going to have to find the force that is parallel to the direction that it's moving. And that's how we calculate the work done. So, okay, let's move on. I've got one more practice problem for us to look at. Practice problem number 5. For this one, I would like you guys to try this one. Okay, this is a complex problem. It's very it's different than what we've done before. I guess that's what I'm trying to say. I would like you guys to try it. Okay, even if you get stuck somewhere, if you try it, I promise you'll learn something as you watch me go through the explanation of it. So please hit pause on your video, try it for a second, and see if you can't come up with the answer. Okay, let's see how you guys did with this problem. Let's go through it. It says a 175 kilogram bobsled. So I'm going to put that right here, 175 kgs. Now, with energy, with these energy and work equations, we don't have a place to put in mass, so I don't think I'll use it, but I'm going to label it anyway. This 175 kilogram bobsled is stopped by a force applied at a 20-degree angle with the ground. Okay, so this is my force that's stopping it. It's at a 20-degree angle relative to the ground. The sled is stopped in 25 meters with 800 joules of work. So I guess this bobsled was going to the right. And somebody is applying a force with a rope to this bobsled to stop it. So that's kind of how I interpreted it. And it took 25 meters, so let's say it comes out here 25 meters in order to stop it. And it took 800 joules of work to do that. Okay. The question says, what is the magnitude of the force? Okay, we're looking for the force in this rope here that's stopping the bobsled. Okay, so I'm really looking for this force. All right, now that we know that, let's go back and write down our equation for work. Work is equal to a force times a distance. Now, we do have work. Let's substitute in the values that we have here. Work was 800 joules in this case. The force we don't know. And the distance we do know, it took 25 meters. Okay? So if we solve this equation now, we'll divide both sides by 25. So divide this side by 25. Over here, the 25 cancels out. And my force is equal to 800 divided by 25. And so my force is equal to 32. And force has a units of newtons. So 32 newtons. Okay, now you might have been tempted and you might have done this and you just circled this as your answer. Okay? But I want to pause for a second and let's talk about that. When you do this equation right here, this force is parallel to the direction that the object is moving. So this force that we just solved for has to be parallel to the direction of movement of this bobsled. So what we just solved for was not this force because it was on an angle. What we solved for was Fx. Okay, so Fx is equal to 32 newtons. And what the question wants is for you to figure out what the force is here on the hypotenuse of this triangle. Okay, so we're really not done yet. So let's use our trigonometry. We have an angle and a side, and we are looking for the hypotenuse. Okay, so remember your trig functions. SOHCAHTOA. If we have the adjacent side, the side right next to that angle, and we're looking for hypotenuse. Adjacent and hypotenuse is right here, so we're going to use the cosine function. So let me try that. Let's do that down here. So the cosine of 20 is equal to adjacent, so we've got to put in adjacent first, which was 32. 32 divided by the hypotenuse. And the hypotenuse is my force that I'm really trying to solve for. I'm just going to call it F. Okay? If I solve this equation now for F, I want to try to get this force off the bottom, so let's times both sides by F. Over here it cancels out. And so here's what I got now. Force times the cosine of 20 is equal to 32. Now to get the force by itself, we need to get rid of this cosine of 20. So let's divide by cosine of 20. And so my force ends up being equal to 32 divided by the cosine of 20. So let's put that in your calculator. And it looks like I'm getting the force is equal to 34.05. And force, the units are for force, newtons. And so there's my answer. A little bit more complicated than I bet you realized. Or maybe hopefully you got 34.05. But this force right here is 34.05 newtons. Okay, very good. So that's all the example problems that I have for calculating work. Hopefully that makes sense, guys, and hopefully those types of problems will be very easy for you from now on. We're not done with the lesson, though. I wanted to talk about a couple of other things with work. And so let's do that now. I wanted to talk about how to calculate work from a graph. Okay? So if we look here, this graph right here, if we graphed a force on the y-axis in newtons, so on the y-axis we're graphing the force, and on the x-axis we graph the distance that the object moves, okay? We can look at this. And so what if it was a constant force? A constant force would be a straight line, because the force is not moving, so it's just going to be a straight line along this point here. Okay, and then we moved it this amount of distance. So really we make a graph and it looks like this. And I asked you to calculate the work done. I hope that you could do that. So work is equal to a force times a distance. So all we're going to do is take the force here, whatever this value is, say it was 10, and say this distance down here was 10 meters. Could you calculate the work? Well, it's really the area underneath that line right there. And so we would calculate that. That area of this rectangle, an area of a rectangle is length times width, so the length would be 10, and the width is 10, so 10 times 10 is equal to 100. So that would be the answer. So hopefully we could do that if I gave you a graph like that. It's just the area under the curve of a force versus position graph. Yeah, so like it says here, the area would be the force times distance, and that is equal to work. Okay, I've got one more graph. Same thing. We're graphing the force on the y and the distance that it moved on the x-axis. But what if the force wasn't constant? What if the force was increasing as the object moved? Okay. A spring force is an example of a non-constant force. It increases as it moves. And so the graphing it would look like this. What if I asked you to calculate the work done by this spring? Well, again, we're still going to take the area under the curve. So you need to find the area of this part of your graph. And it's a triangle now. And remember, the area of a triangle is 1/2 the base times the height. And so let's just put some numbers to it again. If this was 10, and again this was 10, so we're going to take the area is equal to 1/2 the base, so 1/2 of the base would be 5, times the height, which would be 10, and so that in this case would be 50 newtons. Well, and it would be work, so that would be 50 joules worth of work. Okay. So anyway, I don't think I'll test you too much on graphs, but hopefully we could recognize that in order to find work, we take a force times a distance, and then on a force versus position graph, you just find the area under the curve. Okay. All right, one final thing that I wanted to talk about, and let me slide this recording sign out of the way, is that work really is the transfer of energy. Whenever you do work on an object, you've transferred energy to that object. So let's go through this. Work is one of the ways energy can be transferred from one form to another. So there's this principle, a very famous law in science called the law of conservation of energy. Energy cannot be created nor destroyed, but it can change form from one form to another. And one way that you do that is you do work on an object. So consider this spring. Okay, I've got a picture of this one's stretched out, and this one's just at its equilibrium or rest position, and this one's compressed. So if we consider the stretching of a spring, an unstretched spring stores no energy. It's just sitting there. There's no energy to it in the spring at all. But what if we were to grab hold of the end of it and pull that spring and stretch it? So we put a force over a distance. So we've done work on the spring. Well, now we've transferred energy into that spring, and it's called elastic energy. And that's one way that you can transfer energy. Okay? So you apply the force over a distance. Now, what if we take this spring at its rest position and then we apply a force over this distance and compress the spring? We have also transferred energy into the spring. So again, I just wanted to say that work is one of the ways that energy can be transferred from one form to another. So, all right, let's summarize what we've talked about in this lesson. Number one, work can be calculated by this equation here. Work is equal to a force times a distance. Number two, the applied force has to be parallel to the movement of the object. And a lot of times we'll end up taking the cosine, the force times the cosine of the angle times the distance. So anyway, this has to be parallel. The force has to be parallel to the direction that it moves. Number three, the units for work are a Newton meter, otherwise known as a joule. Okay, and joules are abbreviated with a capital J. Number four, work can also be calculated by taking the area under the curve of a force versus position graph. So if you just find the area under the line of that force versus position graph, you will have calculated work. And finally, number five, work, if you do work on an object, it is equal to the energy transferred to that object. All right, so that's a pretty good introduction to energy, what it means. It's the ability to do work or produce heat. It's a pretty good introduction to how to calculate work. Hopefully you learned how to do that in this video. Before we end, I wanted to give you some extra practice in calculating work in physics problems. And so in your student workbook, there is a worksheet called Calculating Work Worksheet. So please go there now and we'll complete that. Again, it's called Calculating Work Worksheet. And hopefully this video helped.